The Interstellar Medium and the Primordial Stars by Christopher McKee.
The interstellar medium is the gas between the stars, and there's almost nothing there. The average density in the interstellar medium is one particle, one atom per cubic centimeter. That's so tenuous that if you were to take just a few liters of water and imagine that the Earth were hollow, and that you just put that few liters of water, you allow it to evaporate and fill the whole interior volume of the Earth, that would be the density of the interstellar medium. So there's almost nothing there. But the galaxy is so vast that actually there's a huge amount of mass in this very tenuous gas. This gas has a number of different parts. The most abundant part is atomic hydrogen. Hydrogen is the most abundant element in the universe, and so it's no surprise that the most abundant thing that we see is just the individual hydrogen atoms. And these atoms can range in temperature from the order 100 degrees Kelvin to up to about 10,000 degrees Kelvin. The atomic hydrogen was discovered many years ago. It was first detected in the late 1940s. And the emission is very interesting. The hydrogen atom emits because there is a spin of the proton and a spin of the electron. And when they are spinning in parallel, that's actually slightly more energetic than when they're anti-parallel. So if you start off with a hydrogen atom in this state and then it goes to that state, it will emit a radiation at a wavelength of 21 centimeters, which is about that big. And astronomers or physicists detected it in the late 1940s. And now we have a huge amount of information about the hydrogen from very large radio telescopes. Another very important constituent of the interstellar medium is what astronomers call H2. Here the 2 is a Roman numeral 2, not a digit 2. And that's ionized gas. The gas is mainly ionized by very hot stars. A star like the Sun emits radiation that is peaked at about the wavelength that we see in our eyes. And the typical energy of a photon is, say, a couple of electron volts. However, when you get up to an energy of more than 13.6 electron volts, then the radiation is energetic enough to actually take the electron from the hydrogen atom and split it away so that you have a separate electron and a proton. And this then makes an H2 region. In order to do that, you need to have a star that's much hotter than the Sun. And the temperatures of stars get larger and larger as the stars get more massive. So when you get to very large stars, such as in the Trapezium Nebula, in the Orion Nebula, you have stars that are up to about 40 times the mass of the Sun, and they create the Orion Nebula, which is visible by eye. Another important constituent then is actually even hotter gas. I should say that the H2 is typically a temperature of around 10,000 degrees. That there's hotter gas that is revealed by its X-ray emission. This hot interstellar medium has a temperature of order 1,000,000 degrees, and it's in rough pressure balance with the colder gas. So that means that since it's so much hotter, it must be much less dense, and the typical density might only be a few thousandths of a particle per cubic centimeter. And this gas then pervades a lot of the disk of the galaxy, but it also extends high up into the halo of the galaxy. In fact, we do not know how much of this hot gas there is far above the galaxy. It's possible that there's as much gas, hot gas, high above the halo as there is in the main disk of the galaxy. Then perhaps one of the most important constituents of the interstellar medium is the molecular hydrogen. This gas is very cold. It typically has a temperature of only 10 degrees above absolute zero. It is concentrated in clouds. Most of the gas is in what are called giant molecular clouds. When you can actually see these visibly, if you look at a picture of the disk of the Milky Way, you'll see a band of stars but there are all these dark patches in them. Those dark patches are generally regions where there's molecular gas. Now, you could say, well, why is it that you have these dark patches? The gas itself, the molecular hydrogen, is not absorbing the radiation. It's transparent. And that's because you have a constituent of the interstellar medium which pervades all the different phases that I've been describing, and that's interstellar dust particles. Much of the heavy elements in the interstellar medium, for example, like iron and silicon, are primarily in solid particles. These solid particles are less than a micron in size. They essentially act like tiny little particles of dirt, if you will. And as you know, dirt, sand, things like that are opaque. So you have these tiny particles. Their size is comparable to the size of the wavelength of visible light and ultraviolet light. And so those particles are very effective at absorbing light, and it's dark. As you go to longer wavelengths, so if I have a little teeny particle, I'm exaggerating here, but imagine the distance between my fingers is the size of a particle. But the wavelength of my radiation is much bigger, then the radiation does not interact very strongly with the particle, and it can penetrate through. And so then in order to study these molecular clouds, we use observations in the infrared region of the spectrum where the wavelength is longer. Many of the infrared wavelengths are blocked by the Earth's atmosphere. So it's been particularly important to be able to use satellites in space, such as the recent Spitzer satellite that NASA launched several years ago. That has made a lot of studies of star-forming regions in the infrared. But I was showing you if a particle was this big, then the infrared wavelengths are this big. Radio wavelengths are far bigger. As I mentioned, in real units, the radio wavelength is, say, for atomic hydrogen is this big. To study molecular gas, you actually want to have wavelengths that are order a millimeter or a few millimeters in size. But then in that case, you would have to have the dust grain would be too small to be seen, and its real size is only about less than a micron. So radio astronomers have been studying these giant molecular clouds for decades, and they have identified many molecules. The most abundant molecule, of course, is molecular hydrogen, and unfortunately, as I said, a molecular hydrogen is transparent. It's almost impossible to observe. Certainly, you cannot observe it from the ground. In space, if the hydrogen is hot enough, then you can see it in the infrared. But you cannot see it in the optical, in the infrared we can see from the ground, or in the radio. So instead, astronomers use the next most abundant molecule in these molecular clouds, and that's carbon monoxide, which is just one carbon atom joined with one oxygen atom. And they can map out all the molecular gas in the galaxy using this CO. And they find that the typical density in these molecular clouds is thousands of particles per cubic centimeter. So that's still an extremely hard vacuum by Earth standards, but very dense compared to the typical density of the atomic hydrogen. And as I mentioned, the temperature of this molecular hydrogen is of order 10 degrees Kelvin. So I mentioned that this dust pervades all these different phases. There are a couple of other things that pervade the interstellar medium also. One is magnetic fields. It's well known that the magnetic field of the Earth, for example, is about half a Gauss. The typical magnetic field in the interstellar medium is about almost 100,000 times weaker than that, 5 or 6 microgauss. When you get into the molecular clouds, then the magnetic field can be somewhat stronger. Another constituent that pervades the interstellar medium is cosmic rays. These cosmic rays were discovered on the Earth early in the 20th century. As people went up in balloons, they noticed that the rate of ionization increased. And now we understand that these cosmic rays pervade the entire galaxy. So you could ask, why is it that the different constituents of the interstellar medium have the temperatures that they do? The temperature of space, of the universe, is about 2.7 degrees Kelvin. That's the temperature of the cosmic microwave background. So why doesn't everything just cool down to that? Well, if you look at the atomic hydrogen that I talked about at first, and as I mentioned, it has this dust that's embedded in it. This hydrogen is heated primarily by starlight. Starlight is, particularly in the ultraviolet, is absorbed by these dust grains, and when an ultraviolet photon comes in and hits a dust grain, it will eject an electron, and that electron carries energy with it, which then heats up the gas. So that's the dominant heating mechanism for the neutral gas. If you get to the ionized gas, as I mentioned, that is also heated by starlight, but in this case by the radiation, which is more than 13.6 electron volts. So what is the origin of the interstellar medium? The gas in the universe was accreted into galaxies, and this is how galaxies are formed. Most of that gas has gone into stars, but we still have gas left in the interstellar medium. This gas is gradually being converted to stars itself. It is believed that there's a continual flow of gas into the halo of our galaxy from the intergalactic medium, and that this gas then is also very gradually accreting into the galaxy. So the galaxy is growing, albeit very slowly now. And this gas starts off and it can be quite hot, but then it cools off when it joins the galaxy. Some of the main questions that we want to understand about the interstellar medium is to try to get a much better understanding of this cycle that I described, where I had starlight that was produced by the stars heating, energizing the gas, then having the gas forming stars. We need to understand this whole life cycle in much more detail. How much of this hot gas is there? If you ask how many baryons there are in the galaxy and compare that with the amount of dark matter, we're actually missing a lot of baryons. On the scale of the universe as a whole, there's about 20 or 25% of the dark matter mass is actually in baryonic mass, but in our galaxy it's less. Where did those baryons go? Some of them could be in hot gas. Some of that hot gas could be in the halo of our galaxy, and it's believed that some of the gas actually has been blown out of the galaxy and is now in the intergalactic medium. But we don't have a very good understanding of that gas yet, because it's very hard to detect. It's has very faint X-ray emission, and it's difficult to measure the X-ray absorption lines that it produces. There's also gas at cooler temperatures, like of order 10,000 degrees there, and that gas can be studied by using ultraviolet observations from instruments such as the Hubble Space Telescope. So in the future, it's hoped that with much more extensive studies of this X-ray emitting gas, we'll be able to get a much better handle on its nature and abundance in the galaxy. Primordial stars are one of the most interesting topics in astrophysics. We have never seen a primordial star, so the field is really driven almost entirely by theory, although at the end of my discussion I'll talk about some observational clues that we can get from looking at them. So the first issue is, what is the difference, what are the key differences between primordial stars and the stars that are forming today? And there are two main differences. The first one is that primordial stars do not have any heavy elements. The heavy elements, such as the carbon, nitrogen, oxygen that we're made of, are all created in the interiors of stars. And we're now talking about the very first stars, so we haven't had a chance to make any heavy elements. So this means that you're talking about star formation that's occurring basically in hydrogen and helium. There's a very trace amount of lithium, but that's so small that it really doesn't have an effect. The second difference is that whereas star formation today occurs when the gas in the interstellar medium accumulates enough so that it can undergo gravitational collapse. In the very beginning, it turns out that the gas was actually fairly smoothly distributed, and it was in the dark matter, which has about 4 times more mass than the baryons do, that it was the gravitational potential wells in the dark matter that seeded the first stars. So the gas was fairly smooth, as I said, and that's because the radiation could freely travel through the gas up to very large scales. And certainly on the scales of stellar mass, then the radiation smoothed everything out. But the dark matter does not interact with radiation. And potential or fluctuations in the density of the dark matter grew from the initial time of the Big Bang and became nonlinear at redshifts of order 100 or so. And gas could then fall into these gravitational potential wells. So as the gas falls into the wells, initially the gravity is dominated by the dark matter, but then as the gas accumulates enough, eventually the gas does become self-gravitating, and it can fall deeper and deeper into the well and become eventually become a star. So as the gas contracts, it is cooled by trace amounts of molecular hydrogen that are produced in the gas. And when the gas gets dense enough, at densities above about 100 million particles per cubic centimeter, then it turns out that you can form molecular hydrogen by a 3-body process where you have 3 hydrogen atoms. So I'll try to do this with my fingers. I have 3 atoms coming together, and then they interact all together, and one of them flies away, taking away enough energy so that the other 2 remain bound as the molecule. So above that density, the gas becomes molecular, and it then is able to cool effectively and continues to contract. A problem that then arises is whether this gas is going to undergo fragmentation. And this is something that is studied through numerical simulations. At the present time, it's not known exactly how this comes out. Some researchers find a great deal of fragmentation, others find less. So a key question is, what is the mass of a primordial star? And this is important for 2 reasons. First of all, if the primordial stars had a very broad distribution of masses, such as contemporary stars do, and in particular, if the primordial stars extended down to masses less than about 8/10 of the mass of the Sun, then such stars would be able to have survived all the way from the time that they were formed, shortly after the Big Bang, till today, and we could see them. We would actually be able to see a low-mass star that had no metals in it at all. No such stars had been seen. So apparently they were more massive than that. It then becomes very important because you could say, well, if the stars are more mass than 8/10 of a solar mass, but less than about 8 solar masses, then they would have died and they would have left behind white dwarfs. And white dwarfs are very difficult to see because they're so faint, and they would have cooled off. So they would essentially have disappeared. But if they're more than about 8 times the solar mass, then they would have exploded as supernovae. And that becomes very important because depending on the mass of this primordial star, when it's large enough to produce a supernova, that can undergo various fates. For some range of masses, in fact, when it exhausts its nuclear fuel, the star just collapses into a black hole and nothing comes out. There are other ranges of mass where the star will undergo a supernova explosion and blow out all the heavy elements that it's created. In fact, there's a particular range of mass above about 140 solar masses in which the star explodes so catastrophically that there's no remnant left behind at all. All the material in the star is blown out into the surrounding intergalactic medium, and this is all in the form of heavy elements. So the mass of these first stars determines whether they're going to wind up being black holes, white dwarfs, or and what elements are going to be injected into the surrounding medium. So what then determines the mass of one of the primordial stars? As I mentioned, these stars are forming in a very large dark matter halo, a deep potential well. The dark matter itself might have a mass of order 1 million solar masses, and it's accumulating gas. And the gas can overcome its internal support due to the thermal pressure when it has a mass of hundreds of solar masses. So you might imagine that the typical star would be of order hundreds of solar masses. So the star is trying to form, and as it forms, it initially starts off at a low mass, like the sun, and it then is producing radiation. As the star grows more and more massive, it produces more and more radiation, and furthermore, the temperature of the radiation goes up. So it's believed that the key thing that occurs is that the star will emit enough radiation that is ionizing the surrounding gas, that it will be able to then ionize and heat that gas to the point that it can no longer accrete onto the star, and that will determine the final mass of the star. So both analytic theory and numerical simulations suggest that you get a range of stars of masses, say, typically going from maybe 50 to several hundred solar masses. All these stars are large enough so that they can explode as supernovae. Some of them might leave black hole remnants, some will explode entirely. And it's a very active field of research then, is to try to understand exactly how these supernovae work, what are the effects of the rotation of the star and affecting the elements that are produced. How is it then that we can try to learn about this today? This all happened over 13 billion years ago. Well, there is an observational clue, and this field has been dubbed stellar archaeology, looking for very, very old stars, not the first stars that formed, since they formed with no heavy elements, but the second generation of stars. Those stars actually incorporated the heavy elements that were made by the first stars. And as I described, we can tell or infer what the mass of those first stars was from the pattern of heavy elements that are produced. So astronomers are doing very large surveys of hundreds of thousands of stars, looking for stars that have a very low metal abundance. And by metals, I mean not just metals in the way that we refer to them, but in astronomical lingo, that is stars, metals refer to just heavy elements in general. And astronomers have found that there are many stars that have, for example, iron that's 1,000 times less in these stars than the sun. They found some that have 10,000 times less, even more than 100,000 times less. And I think now there's even a claim that there's one that is more than 10 million times less than the iron in the sun. An interesting feature of these stars that is not fully understood yet is that even though they have this very, very low iron abundance, they do not have very low carbon abundances. So their carbon abundance is generally at least about a thousandth or maybe a 10,000th that of the sun. So that if you then look at the ratio of the carbon to the iron, then as you keep on going down and down in iron abundance, the ratio of the carbon to the iron gets larger and larger. And that is a very interesting clue as to the nature of these first stars. There are the large surveys will eventually be able to resolve this issue and determine, I think, fairly unambiguously what the nature of the first stars is.
the virtual universe and our home supercluster.
We know what the universe looks like today, and we have a pretty good idea how it started. With the Big Bang. But what happened in the 14 billion years between the Big Bang and now? How did galaxies, like our Milky Way, evolve? To test our theories, scientists at MIT have built a computer model of the universe. A simulation so complex that calculating it on a single desktop would take 2,000 years. They modelled a volume of space almost 350 million light-years across, a large enough chunk to be representative of the whole universe, but detailed enough to delve into individual galaxies, a feat no other team has managed. The model doesn't just tackle the universe's huge range of scales. It also richly describes the forces at work, much better than previous attempts. By factoring in the laws of physics, and a variety of theories about how gases cool, stars evolve and black holes grow, the model recreates both the galaxies and stars we can see, and the dark matter and dark energy that we can't. The simulation starts just 12 million years after the Big Bang, when things start to get interesting. Dark matter clusters together under the force of gravity. If we could see it, it would look like a web. In fact, scientists call it the cosmic web. Where dark matter is densest, shown as bright pink spots, ordinary matter also clumps and forms into galaxies. Now we're looking at the ordinary matter. Blue shows relatively cold clouds of gas, where stars form. Green is warmer gas, while red and white show hot regions around the most violent galaxies. Supermassive black holes grow at the centre of these. As they gobble up matter, they superheat the material around it, blowing out gas in these violent white bursts. Over time, this enriches the space between galaxies with warm but sparse gas. The simulation also shows the distribution of different elements. The early universe was full of helium and hydrogen. As stars evolve and die in supernovae, they fuse these basic chemicals into heavier elements, such as carbon and oxygen, as well as metals. The violent bursts around black holes spread these elements across space, the pink clouds you see here. Life depends on these chemical building blocks. Only when you have enough of them do planets and complex molecules form. We're looking at dark matter again, and we've almost reached the present day. 14 billion years of the universe's evolution has pulled a tightly woven dark matter web into a looser network of giant galaxy clusters. A big challenge, the team say, was recreating the variety of galaxies we observe. The model's 40,000 galaxies include this spiral one, like our Milky Way. In fact, the simulation produces a world that's remarkably similar to the real universe, as we see it through our telescopes. And because the simulation matches our observations so well, it gives us greater confidence in our understanding of the universe. How it began, how galaxies formed, what it's made of, and the laws that govern it. Of course, the model is not perfect, but where it fails, the simulation challenges our view of the universe. It begs the question, if our descriptions don't match what we see, what might we yet be missing? Somewhere in the universe is a small blue planet, the third rock from a star called the Sun, just one of billions of stars in a spiral galaxy known as the Milky Way. But where in the universe is the Milky Way? A team of scientists gathered data on more than 8,000 of the galaxies that surround us. They mapped each galaxy's position and movement in space. And, for the first time, they've shown that the Milky Way is part of a much larger system of galaxies, a supercluster that they have named Laniakea. The Milky Way is nested in the furthest reaches of this structure, on the outskirts. The entire universe can be seen as an intricate network of galaxies, a cosmic web. Some areas are almost empty, dark voids. Others are densely packed with galaxies in regions known as superclusters. Superclusters are the biggest structures found in the universe, but scientists have struggled to define where one ends and another begins. To map our home supercluster, a team led by Brent Tully at the University of Hawaii studied the motions of the galaxies around us in unprecedented detail. Even though the entire universe is expanding rapidly, gravity is also at work, pulling against this acceleration. By discounting cosmic expansion, the team worked out which galaxies are being pulled towards us, shown in blue, and which are being pulled away, shown in red. This enabled them to create a map of cosmic flows, the paths that galaxies migrate along, tugged at a tiny pace by the force of gravity. Using this motion, they came up with a new way to map the distribution of matter in the universe. Delving into our home supercluster, you can see that most galaxies are being pulled towards a dense centre. This is known as the Great Attractor. Our galaxy is among those sliding towards this patch of space, which dominates our region of the universe. Let's take a different view. Each circle represents a galaxy. Again, we can see most galaxies being pulled towards the Great Attractor in the direction of the arrows. Between the Great Attractor and us, the Milky Way, there's a relatively empty area, a blue void. And next to us is Virgo, a large and dense cluster whose bright galaxies have been observed from Earth for centuries. Until now, astronomers grouped us, the Milky Way and its surrounding galaxies, with Virgo and nearly 100 other clusters in a supercluster that stretches 100 million light-years across. But using this new technique, we can see that this is just the tip of the iceberg. This cluster of clusters is merely an appendage of a much larger supercluster, more than 100 times bigger and more massive. But how did the team know how to redraw the boundaries of this cosmic map? Here's our supercluster in black, and a neighbouring structure, Perseus Pisces, in red. Scientists defined the boundary as the points where the flows of galaxies diverge, like water dividing at a watershed. This is where neighbouring structures shear apart. This is the first clear definition of a supercluster. Laniakea means immeasurable heaven in Hawaiian, a fitting name for the vast community of galaxies that we are a part of. So now we know that on the edge of a supercluster called Laniakea, in a galaxy called the Milky Way, around a star we call the Sun, there is a small blue planet, our home.